Hi everyone. Today let's talk about session 2.3, resolution proofs. Resolution is a proof technique proposed by Robinson in 1965 that depends on a single rule. If P or Q and not P or Q are both true, then Q or R is true. Okay, so to understand this, let's consider the following truth table. So we have the P, Q, R. Remember, each of them we can have true or false. So two choices for each of them. So 2 times 2 times 3, 2, we get 8. We have 8 different possibilities. And how do you write the truth table? You put 4 of them is true, 4 of them are false, and then you have 2, 2, 4 false, true, true, 4 false, and then for the R, you have true, false, true, false, true, false, alternate. Then you can have 8 possibilities. Okay, let's look at P or Q. So P or Q is if P and Q are both true, then it is true. And actually, as long as one of them is true, the answer is gonna be true. Okay, and it's only false when both of them are false. So if P and Q are both false, then P or Q is false. Next, not P or R. Okay, so not P, well, not P, all of these, not P is false, or R is true. Okay, this is true. So this guy is true when R is true. So let's figure out, okay, where are the R's true? So here, here. Okay, and then you also see this guy is true when the not P is true. Well, not P is true when it means R is false. Well, R is false is right here. So we get this as well. And for the remaining, this guy we get false, or false is false, false of course is false. So that's why you have this. Okay. And then Q or R. Q or R is false if both of them are false. So when do we have both of them are false? Right here. When do we have both of them are false? Right here. So that's why the rest is true. Okay, so here are the truth tables. And let me see. Okay, let's emphasize. We want to see if P or Q and not P or R are both true. So when do we have them both true? We get this guy and this guy. True, true. And this guy and this guy. And that's it, right? Notice that those 4 cases, if the P or Q and not P or R are both true, you see the Q or R is always true. So that's why we get this claim follows. Okay, so this is true. Okay. Because resolutions depends on this single simple rule, it is the basis of many computer programs that reasons and prove theorems. In a proof by resolution, the hypothesis and the conclusion are written as clauses. A clause consists of terms separated by ors, where each term is a variable or the negation of a variable. So in the clause, you only see 2 logic symbols. You only see the not and the or. Okay, only 2 logic symbols. You're not supposed to see other logic symbols like and or implies. Okay. Alright, let's look at the following example. Is the expression A or B or not C or D a clause? Yes, because we only see or not, right? And then part B, is the expression X, Y, or W or not Z a clause? The problem is here we have 2 variables instead of a single variables. So each term between the not or there should be only 1 variables. And in many notation, x, y. So in many notation, if people don't write anything between them, x, y is actually means x and y. Okay, in many notations. So that's why, because we don't want to see and there, so that's why this is not a clause. Okay, next is the expression P implies Q are clause. Of course not. This is the indications. So that larger symbol is not allowed in the clouds. We need to see or not. Okay. All right. Let's continue. Example, prove the following using resolution. So resolution, resolution, let me recall, is P or Q. When you see P or Q and not P or R, you can combine them and you get Q or R. Well, how do I think? Well, I remember as like this. You see the P and not P, they kind of cancel out, so you only left with Q or R. Okay? So this guy is called resolution. Okay, this is resolution. Okay, so now let's look at our example. So remember, when you prove the arguments, you're gonna number the lines. Okay, when you have a new proposition, you can number it as well. So let's look at the first two. A or B, not A or B or C. Well, A kind of cancels, so we get B or C. And this is from line number 1 and 2, right? And we're using the resolution proof, okay? And next B or C, but we also have not C or D. So see, the C kind of cancel. Then we have B or D, and this is from 3 and 4. Okay, and the rule, they're both using resolution. Okay, and yes, in our example, we proved the following using resolution. So that's why we this is how we get the conclusion. So far, so good, everybody. Okay, so here I have some remark. Special cases of the resolution that follows. If P or Q and not P is true, then think about it. Either P or Q is true, but not P, then it must be Q is true. So this is some special case of resolution. And the other one, P and not P or R are true. Well, P are true, so not P is false, but not P or R is true. Then it must be R is true. So far, so good, everybody. Okay. So these also count as resolutions. So resolutions, we can have this one or this one or this one. We can have 3 of them, okay? Let's continue to look at this example. So A, not A or C. Okay, so we can put it here. A is true, then not A is false. Then because not A or C is true, then it must be C. So this is from number 1 and 2. We get C is true. Okay? And then, because C is true, then not C is false, then but not C or D is true, then D must be true. So here we get D is true, and this is from 3 and 4. Okay, and we are all using resolutions. So far, so good, everybody. Okay. Next. If a hypothesis is not a clause, it must be replaced by an equivalent expression that is either a clause or the end of clause. Okay, what is this? Consider the following De Morgan's laws. Okay, so we have not A or B. Well, what is that? It will give us not A and. Remember the not flip the and or. So and not be. I told you before as a notation, if it's and, then you can don't write the and. It becomes not A times not B. And we have not A, B. So this is like not A and B. That's not A or not B. So far, so good, everybody. So that's why if you see and, you can actually express this in terms of or not. Okay. And we also have the distribute law, A and B, C. So this is A or B and C. We can distribute. So we have A or B and then and A or C. So it's A or B and then and A or C. So far, so good, everybody. Okay, keep these in mind. Let's continue. Okay, the first one, A and not B, C. Okay, what is this guy? Well, this guy is equivalent. So this guy, let me put, it's equal. It's equal. It represents not B times C, so it's an and. So which means we compute these guys first. So far, so good, everybody. And this guy is equivalent as A, so we can distribute A and not B, and then and A or C. Okay, everybody? So if you see an and there, you can actually separate these guys as two lines. Here, we put all the things in different lines. Actually, when we come up with the conclusion, we mean this guy happened and this guy happened, then we have this conclusion. Okay, so here you see the two clauses are separated by the and, then you can put those two clauses in different lines. Okay, same thing here. This guy is equivalent to not A, and then the or becomes and, not D. See, you see those two clauses are separated by the and, then you can put them in different lines. So we can rewrite the problem. We have A or not B, we have A or C, and we have not A, we have not D. Okay, and we want to get the conclusion not B. So let's label them 1, 2, 3, 4. So far, so good. Okay, so now let's start to solve the problem. Okay. The good thing about separating the clauses, it makes it the expression has less variables and it's easier to compare them. Okay, so here we can see, oh, not A. Let's look at the A's. Well, we have this guy and this guy. So first, let's look at, so 1, 2, 3, 4. Then this is 5. Let's look at 1 and 3. So not A is true, then A is false. If A is false, then not B is true. Oh, let's see. Oh, okay. we actually get it. We actually get the conclusion. So from 1 and 3, we already get the conclusion. So in this case, number 2 and number 4, we don't need them. It might be the cases that you have some clause that you didn't need to use them. This could be the case. Okay, so let me put down the remark here. Okay. Remark. When you see and in the expressions, we can separate the clauses into different lines to make the expressions more simple. Okay, and during the proof, there might be some clauses that you didn't use it. So it could be the case some clauses don't need to be used. Okay. Yeah, it's good that every time we learn an example, we can come up with the summaries, what we learned from this example here. Okay. All right, let's continue. Okay. So, we call in chapter 1, okay, when we talk about implications, actually I showed you a truth table and I showed you that P implies Q and not P or Q, they are equivalent. And then P, if and only if Q, is equivalent to not P or Q and P or not Q. Okay, so yes, keep this in mind. This is in session 1.4, 1.3. Okay. All right, so let's look at our example. So we want to show it. 1, 2, 3, 4. Okay, let's label them. And let's see. We want our results in terms of STU. So which means for the other variables, we want to eliminate it. Okay, so first of all, we can eliminate P. You see P here and not P there. So we do number 5. Not P and P, we can cancel them. Then we have T or Q or R or U. And this is from 1, 4. So far, so good? Yeah, so we can cancel them. And then, oh, I can cancel the Q. So the number 2 and 5, we can cancel the Q. Then we have S, T, what's left? R, U. Okay, and furthermore, 3, we can cancel the R. So see, this R and 3. So from 6 and 3, we get the R cancel. So we have ST or S or T or U. Okay, what is ST? Well, you know that ST is actually S and T. Well, this guy is a subset of S. Do you agree? Yes. So that's why if we have okay, not really a subset, but if S and T happens, then S happens. So the S already included S and T. Okay, so that's why ST or S. This is just S. Well, the S will actually eat the ST. Okay, so this guy is equivalent to S or T or U. Okay, because the prepositions S and T, it means S is true and T is true, so it means S is true. Okay, all right. Let's continue. Okay, so now we have shown our results. Okay, let's continue. So P if and only if R and R. Okay, so first let's rewrite the problem. So what's P if and only if R? That's not P or Q and P or not Q. Okay. This is equivalent not P or Q and P or not Q. Okay, because it's and, then we can rewrite the problem into different lines. We can have not P or Q and P or not Q, and oops, sorry, is R there. So let's replace Q by R. Our variable change. Oops. Okay, so and we have R. So therefore P. Okay, so this is our new problem. Let's solve this problem. Okay, what do? Label them. Number 1, 2, 3. Okay, so now we see R is true. So that's why from the line number 2 and 3, because R is true, then not R is false. Then the P has to be true. So we only use these two clauses. We can get the conclusion. We didn't need to use the number 1. So far, so good, everybody. Yeah, it could be the case that we only use some clauses, but we didn't use all of the clauses. Alright, so that is session 2.3. So please go ahead and do your homework, and if you have any questions, feel free to ask me. Have a nice day. Bye.